This is my demonstration for the project closest pair problem. To run this project, you need to install Matplotlib, Pandas, and IPython. So this is how you install it. This is important for you to be able to see the tables and the graphs. So I started the project, create some helper functions. The first one is the one that creates random numbers from random points from 0 to 100, and these points are guaranteed to be unique. Then you have a merge sort. Merge sort is used by divide and conquer algorithm, and merge sort is guaranteed to be n log n. Um, and this is based on the book Introduction to Algorithms, and the pseudocode is this one. So pretty much it's exactly exactly the same algorithm. And then I have this function that allows me to sort tuples using the merge sort. So as a merge sort is meant to be used by integers arrays, and tuple is x and y coordinates. So this helps me use the merge sort algorithm. Okay, so then I go to the two main algorithms here. So the brute force approach. The brute force approach compares each point with all the other points, and then we record the ones that has the minimal distance. The further distance we use Euclidean distance, and we return the pairs and the distance. So I'm returning the distance here because sometimes when I'm printing the logs comparing brute force with the divide and conquer, the points are different. This happens because it may happen to have multiple points with the same distance. So I also return the distance because then we can guarantee that both algorithms is returning the same result. Cool. And this is the pseudocode. The difference is that I am returning the pairs instead of the index. Professor says that this is okay. Then we go to recursive approach. So we start by sorting the elements. So they are, as I said, merge sort. So it's n log n. And then we call the recursive function. The recursive function base case is this one. And then we construct qx, rx, qy, and ry. The construction is pretty straightforward. So for the qx, we just get the first half of px in the second half of the py for the rx, and then we get the x star, that is basically the dividing line. The x star is the last element in qx, the x coordinate. So this is the dividing line. With the x star, we are able to construct qy and ry, and pretty much you get py, the x coordinate of py, and compare with the x star. If it's smaller, it's a qy. If it's bigger, it's ry, right? Professor mentioned that we can use a flag array, so I did this code using a flag array as well, but I think this is way slower. So this is more straightforward, easier to understand, and faster, right? The pseudocode don't determine how we can construct, so we are free to use whatever technique we want as long as it's linear time. That is the case here. So this is linear time. Okay, so and then we call recursively multiple times, and after we process the whole stack, we have the smallest point on the left and the smallest point on the right, and then we calculate the delta because eventually you can have elements between the lines, right? It's between the two groups. Eventually you can have elements with the with the smallest distance. So the delta, we have what is the smallest distance, and then with the smallest distance we get a list of elements that is between the lines and within the distance, delta distance, right? With this list of elements, we search, and then we look for the next 15 elements on this list to see if eventually there is one that is smaller that we have found until now. If we found them, we return the best pair and the minimum distance as well. So that's the general idea here. and the confusing part can be this one because you can think this is quadratic time, but in fact is linear time because this is only for the 15 numbers, and this is a 15 number is a 15 is a constant, so this is guaranteed to be linear time. All right. So I create this algorithm here just to make the comparison, and then I have one here that create the tables, right, with the empirical time and predicted time, and then here we create the plots, right? So if I run this algorithm with a small number of elements to be quick, we're going to see that we are logging all the interactions and the averages and for each one. So you're going to see that um, the distance is always the same. Like for example, this one, divide and conquer is always the same, but eventually you can have different pairs if they are the same distance. And then we have the table. This table compare initially. The first table is uh, to compare the brute force, right? And in the end of the table we have the constant, and be aware that the constant is in scientific notation, and here the ratio is not. So that's something to be aware because I decided to write like this, then I have more precise predicted runtime. And then this is another table for the divide and conquer, the same idea, and those are the graphs. So this is the comparison between both algorithms, and this is empirical versus predicted running time. And this concludes the project, and thank you for watching.